Greetings to all and welcome to this lecture. We are in module 7, lecture number 4, single piece model. In this lecture, we will discuss that can we define a single piece model which captures the effect of weak, strong and moderate inversion, because we know the modeling of moderate inversion is somewhat complex. We will also discuss the advantages and disadvantages of source versus body reference model. These are the learning outcomes of this lecture, which helps you to understand how we compare the moderate inversion single piece MOSFET model with separate regions of model in terms of continuity and analytical simplicity. This will help you to understand that how we can frame a single model which defines all region of operation at somewhat accurate, meaning weak, moderate and strong inversion by using a single piece model. Let's start this lecture with a quick recap. In previous lecture, we have discussed thoroughly about weak inversion of operation. We said that when we applied VGB in such a way or VGS in such a way that the channel at the source and drain end are weakly inverted. So, we do not have enough charge carriers, right. At that moment, the surface potential here is psi S0, the surface potential here is psi SL. We argued on 2 points that throughout the channel the surface potential is almost constant, which is nothing but psi SA at source side, and at drain side also it is psi SA, and hence there is no drift component present into the channel. The current is predominantly captured by diffusion component. We define that current equation as IDS is equals to W divided by L mu into phi t Qi L dash minus Qi 0 dash. Then we said that we can reframe these equation in terms of terminal voltages as VDB and VSB, which gave us two idea in terms of body reference and source reference. If we talk about source reference, we got that the current is approximately related with some constant into e to the power of VGS minus VT divided by n times of phi t into 1 minus e to the power of minus VDS divided by phi t. We have plotted two graphs, one with respect to ID and VDS, one with log ID versus VGS. Both graphs gave some intuition about the weak inversion of operation. One, if we increase the VDS, then this exponent will disappear after a short increase of VDS, and ultimate the current will remain constant and it becomes a function of VGS. Now, when we increase VGS, let us say VGS1, VGS2, VGS3 and so on, this difference between the current is exponent. It is not quadratic, what we have discussed in strong inversion. The another part of the weak inversion is can be calculated or is can be analyzed as log ID versus VGS. When we plotted this, we found that this curve is almost linear because of having exponential dependence. We are taking log, so it is almost linear, and this is called as subthreshold slope. The subthreshold slope can be defined as the rate of change of gate to source voltage to change a decayed value of current, log of IDS, this is log 10. So, this is subthreshold slope, and we said that minimum limit of the subthreshold slope for a conventional MOSFET is 2.3 into n into phi t. Considering n is equals to 1, this will give you 60 millivolt per decade. Now, let us move forward and see, can we define the moderate inversion region, or can we define a single piece model which captures all region of operation, meaning the weak inversion, the moderate inversion and the strong inversion. So, can I define some set of equation which relates with a proper continuity between this weak, moderate and strong inversion model, right. So, to move further, we will actually calculate the relation between charge and the current in weak and moderate inversion, right? Whether it is exponentially dependent or it is linearly dependent or what. So I should not write exponential, I need to write what is the function of charge given by or related with current. First, we need to take care about these things, like in moderate inversion, diffusion and drift both contributes significantly, and hence we cannot ignore one of the current component, either IDS1 or IDS2. We need to consider both. Moderate inversion is hard to model because neither strong inversion nor the weak inversion models alone work. We need to take care about the proper continuity also between weak to moderate, moderate to strong. Equation must ensure that IDS continuity across weak to moderate, moderate to strong boundaries. Further, the derivative of the current IDS versus delta VDS should also be continuous, right? So we need to define a set of equation which follows this also. The second is we need to tune the parameters, which is in our hand, in the sense that threshold voltage, phi naught, alpha, such that there is a compact model can be drawn which captures all the region of operation. So let's do some exercise to find out how the current and the inversion charge related in different region of operation, at least the region of operation which is well defined, meaning the strong inversion and the weak inversion. You remember, in strong inversion we said that the current is predominantly dominated by drift component, which was denoted by IDS1 is equals to W divided by L mu into integration of minus of Qi dash d psi s between psi s0 to psi sl, and then we linearize this inversion charge. Qi dash is equals to alpha times Cox dash into psi s, and we replace this variable as dqi dash divided by alpha into Cox dash is equals to d psi s dash, d psi s, right? So the current was nothing but W divided by L into mu divided by alpha into Cox integration Qi 0 dash to Qi L dash with minus Qi dash dq. When you solve this equation, ultimately you will ended up with this formula, which says that in general my current, which is a drift component IDS1, directly proportional to inversion charge square, right? So again we are just mentioning that how my charge and current are related. So I can simply say my current is directly proportional to inversion charge. Obviously there are the charge inversion charge difference is present, but in general I am considering it is directly proportional. The second thing is, we know that the drift current equation in strong inversion is can be given as IDS, let us say IDS dash is can be given as W divided by L into mu into Cox dash Vgs minus Vt whole square divided by 2 into alpha. So I can simply say this IDS is directly proportional to Vgs minus Vt whole square. Seeing both the equations, I can simply say that the inversion charge is directly proportional to Vgs minus Vt in strong inversion. This is what it's giving, right? So IDS is directly proportional to square of Qi dash, and IDS is square directly proportional to square of Vgs minus Vt. So I can simply say the inversion charge is directly proportional to Vgs minus Vt, or inversion charge is linearly changing with Vgs minus Vt. Let's see what is the case in weak inversion. As we have discussed in previous lecture, that in weak inversion the diffusion current dominate and there is no drift component, correct? And hence the current equation, which was given as IDS2 is equals to W divided by L mu into phi t into Qi L dash minus Qi 0 dash. This is a relation between current and the charge. Now how can a current with respect to voltage is related? That is also we have seen in previous lecture that it is exponentially related, meaning current is exponentially related to Vgs minus Vt divided by n times of phi t. So if I want to represent in terms of charge and voltage Vgs minus Vt, it is exponential dependent, right? So by using this understanding of strong and weak inversion, in between there will be a moderate inversion. Can I use some equation to fit like that it will capture both the effect? So let me define a dummy charge equation which says that Qi0m and Qilm. Here m stands for moderate inversion. So I am just defining as a dummy charge or dummy equation, charge equation, which relates between the boundary of weak inversion and strong inversion, right? And in between there will be a moderate inversion, correct? So this is the equation I am following, where W by L into phi t into Qi0 dash square m minus Qi dash L dash m square, right? Now if I want to use this, then I can directly use the strong inversion model because the current is square dependent on charge. But suppose if I want to use this, then how can I rewrite this equation in terms of square? So this IDS2 can be written as IDS2 can be written as W divided by L into mu into Qil dash to the power 1 by 2 to the power 2 minus Qi0 dash to the power 1 by 2 to the power 2. Again, now you see this equation, again current is dependent upon square times of charge, though yes, this charge is dependent on 1 by 2 power. Similarly, this current is dependent on square types of charge. So I need to define a function which relates this. Let us use a soft plus function and see the property of soft plus function. This function says if this x is small, then log of 1 plus e to the power x is almost e to the power x, and when x is larger, then log of 1 plus e to the power x is x. How this soft plus function is helpful to us in this regard, that if you see, if I define a charge equation, let us say Qim as log of 1 plus e to the power x, right? So x, what I am taking is Vgs minus Vt divided by n phi t into 2, because here Qi dash is what? Half to the power 1 by 2. If you take 1 by 2, it will be 2. So if I define, instead of x here, if I write Vgs minus Vt divided by 2 times of n phi t, right? Then this equation, when x is small, so in weak inversion what happens is this term small, and if it is small, ultimately this function will give me what? E to the power of Vgs minus Vt divided by 2n into phi t. That is what Qi dash I will get. For weak inversion, I will put back here and I will get the same current equation which is valid for weak inversion. Now what will happen for strong inversion? For strong inversion, x is large. If x is large, this function will give me what? X. So e to the power x, what I have taken? Vgs minus Vt divided by 2 into n divided by phi t. So when x is large, this function will give me this value, but what I am actually expecting? Vgs minus Vt. So I need to multiply with 2 into n into phi t outside, correct? And then I need to define log of 1 plus e to the power this, because when you solve this for x large, then this will give you Vgs minus Vt divided by 2n phi t, and this 2n phi t will get cancelled. Ultimately you will get this what? This equation. So I can simply rewrite all this exercise in one equation, that is Qim can be defined as 2n phi t log of 1 plus Vgs minus Vt divided by 2n phi t. I think it is clear why we define this soft plus function in such a way, because this will give me different values in weak and moderate inversion. And how it will connect? Again, I will go back to the same formula of current equation. IDS is equals to W divided by L into mu into COX dash, right, into QI ML dash square minus QI, this was 0 and this is L dash square, correct. Here if you see this term having 2n phi t and earlier this term was having phi t. So phi t square is coming up, 2n is coming up from here, W by L mu into Cox is coming from the previous equation, and there are two component. One is log of 1 plus Vgs minus Vt by 2n phi t. This is at source side and this is at drain side, right. If you see carefully, in the drain side we do have another term n times of Vds is coming. This shows that the factor n Vds shows that when you increase Vds, this factor will decrease, right, and hence the gate should be applied n times higher to compensate this effect, and hence this n times of Vds is coming into picture, right. Now what will happen when you increase this Vds? It means in the MOSFET you are increasing Vds. It means at this edge you are going to weak inversion or depletion. However, this is in moderate inversion. So ultimately you can say my device is in moderate inversion, but this factor will disappear, because if you increase Vds, this factor will disappear, correct. So you can simply rewrite a single form of equation which holds good everywhere. So this is the single form of equation which at least hold very good in strong inversion. And in general, the circuits, in analog circuits we talked about the strong inversion of operation, so we can model that region of operation by using this equation, which simply captures the adjacent effect of weak inversion, moderate inversion and saturation effect, saturation region of operation precisely. Now let us see what is the difference between source and body reference, what we have opted in our previous analysis. We said that we are basically having 4 terminals, one is gate, one is drain, source and body. There are two possibilities. One, we can take body as a reference, and one we can take source as a reference. If we are taking body as a reference, then VGB, VDB, VSB are the independent variables, and if you take source as a reference, then VGS, VDS and VSB are the independent variables. Both modeling approaches are theoretically equivalent, right. It means the difference between two approaches arises mainly from the practical implementation of these models. It is not about the theory. We also saw one transition, that if I really want to represent of one reference model in terms of other reference model, I can use that VGB is equals to VGS plus VSB, or VGS is equals to VGB minus VSB. The similar hold good for drain side, VDS is equals to VDB minus VSB. So this is also good that a body reference and a source reference model can be converted into each other by simply replacing with this, right. So advantage of any one model can be transferred to other model by using proper transformation. Let us see few of the properties of source reference model, or we can say why the source reference model is preferred. The first point is, if you see the geometry of the MOSFET, you do have a gate terminal, a source terminal, a body terminal and a drain terminal. Let us consider you are fixing the gate to source voltage and you are changing the source to body voltage, correct. Then the effect in the channel will appear in terms of threshold voltage, however the impact will not such high. However, if you keep this VSB as fixed and change VGS, then the impact in the channel causing inversion, depletion and so it will be high. Thus the impact of VGS is higher as compared to the impact of VSB. In addition, suppose the body substrate or the substrate doping is lowered. If the substrate doping is lowered, you saw that gamma, which is a body effect coefficient, which is given by 2 into q into Na into epsilon divided by Cox dash, right, it will be lowered. If that factor will be lowered, the variation of VSB on Vt will be lowered, because Vt was be given by V flat band voltage plus phi naught plus gamma times square root of phi naught plus VSB. That is what the impact of body voltage is relatively less as compared to the impact of source voltage, or the impact of gate to source voltage. That is what we will prefer the source reference model instead of body reference model. The second advantage of source reference model is, which is historically related, as all the devices what we have read so far, like triodes, BJTs, they are having 3 terminals, right, like emitter, collector and base. In addition to this, so following the same trend, MOSFET does also have 3 terminal where body is kept constant or tied to source. So we do have drain, source and gate. The input is applied between gate to source and the output is taken from drain to source. That is what we follow. So historically also the body reference model is advantageous. The another part is, we have seen in our previous analysis, when we thoroughly analyze the surface the source reference model, we saw that Vt term, the threshold voltage terms, is coming automatically in the equation, right, we need not to bother about. However, Vtb is not coming up. That is what the equation which is captured in source reference model as Vgs minus Vt whole square, or you can say Vds minus alpha into Vds square divided by 2, correct, into W divided by L into mu into Cox. This is a current equation where Vt is automatically coming into picture. So if we change the body reference, we need to again define this value in other sense. So to definition of threshold voltage is also well defined in terms of source reference model. The another is, in some devices what happen, the substrate is separated by a box layer, a buried oxide layer, right, and this can be treated as another gate of the device. So this is, let us say, source, this is gate, this is drain, and you have a gate this side. So if you measure this voltage with respect to body, ultimately you are killing this terminal. It's better you measure this gate voltage with respect to source and use this terminal as another gate terminal. So you can use this device as a double gate devices, right. In that sense also source reference model is preferable. In another applications, you can think like, in some devices source and drain are not symmetric. In some devices the shape of shape of drain region and source regions are not symmetric, and hence to find out which terminal is source, which terminal is drain, you need to keep one terminal as a reference, and that terminal is what? Source reference model. So we do have another advantages of body reference model too, because the body reference model gives a new intuition which inherently capture the symmetricity of the device, meaning if you have Vs here and Vd here, then body terminal actually maintain inherent symmetry of the symmetric MOSFET. The symmetrical behavior of well laid out MOSFET can be effectively utilized in analog circuit designs, where this body reference model will be used. In long channel body reference model, the current saturations occurs at the value of VDB, right, that are independent of VSB, which agrees with the basic device physics and simplifies the analysis. Yes, the weak inversion of operation is well defined in terms of body reference model. We have also seen that when you want to relate a relation between IDS versus VSB, then we should use the body reference model. The source reference model will not give you an intuitive understanding. Effects related to the transverse field, the effective carrier mobility, which we are going to discuss in subsequent lectures, is well defined using body reference model. A few of that this smooth current behavior is especially important for simulating sensitive analog and mixed circuits, whereas source reference model may sometimes introduce a convergence issues in well defined TCAD models. So let me summarize this lecture. In this lecture we have found that we can define a simple piecewise model which actually captures all the region of operation, that is weak, moderate and strong. We also said that moderate inversion is modeled using continuous analytical forms that smoothly connects weak and strong inversion behaviors. A single piece model we have derived using soft plus function, which is defined as log of 1 plus e to the power of x, which gives the value of x when it is larger and it gives e to the power x when x is smaller. Then we said that what are the advantages and the specific operations where the source reference and body reference models are preferred. Like we said that in weak inversion the body reference model is preferred, and it will give you a good understanding when we discussed the weak inversion of operation with reference to body reference model. So we'll stop here for today. Until then, take care.